这麦克风是哦，对对对对，这不用
没反应。
会，还有点。
The cost and time of 3D printing grow cubically with respect to an object's scale. To fabricate a large object, the cost and time of 3D printing grow cubically. The cost and time of 3D printing grow cubically with respect to an object's scale. To fabricate a large object, it has to be partitioned into smaller parts for printing and assembled later. We present a coarse-to-fine approach for cost-effective fabrication of large objects. An input 3D model is represented by a coarse interior polyhedron base and a fine exterior shell. The polyhedron base is produced by 2D laser cutting by assembling planar plates with well-designed joints. The exterior shell is fabricated by 3D printing and then attached to the bases. Our approach significantly reduces the fabrication cost and time. The assembled object can be repeatedly disassembled and reassembled, facilitating storage and transport. The fabricated object can stand by itself. To approximate a 3D shape using an inscribed convex polyhedron, we start with a simple cuboid. We optimize its vertex positions to maximize its volume while fixing its topology. Next, we modify the polyhedron's topology using planar cuts. Then, we iteratively optimize the geometry and topology of the polyhedron. Various constraints, such as assembly, aesthetics, symmetry, and balance, are enforced in the optimization. For the complex shape shown here, we segment it into a few quasi-convex components and approximate each component with one convex polyhedron. During the optimization iteration, we enforce one more constraint for two neighboring polyhedrons. We construct an interlocking laser-cut base from each optimized polyhedron. Our method iteratively explores polyhedral corners to create local interlocking groups with non-orthogonal joints, and links the groups into a network to construct a tightly connected laser-cut assembly. By using printed rods and screws, 3D printed shell parts are then attached onto the laser-cut bases. We assemble the laser-cut parts of a Max Planck model following a certain order. The parts interlock with one another through the designed joints, forming a steady assembly. Now, we assemble the other laser-cut base. We attach the 3D printed parts onto the bases and connect them using printed rods and screws. Lastly, we put the two part assemblies together. After tightening the screws, we put the key part in the assembly.
Alright, that's the video today. I would like to invite someone to summarize this video for us. Anyone? What is this technology about and how to do it? What kind of problem it encountered? Okay.
We use computer to create three-dimensional models to simulate the structure and the shell of object. And finally, use three-dimensional creators to create this part, and
Okay.
make it make it to the original object.
Okay. Technically, this method is called coarse-to-fine fabrication of light 3D objects. Could you explain a little bit what is the process coarse-to-fine fabrication? Do you know the keyword coarse to fine means? Okay, that means it starts from a very rough shape, but finally it can be improved to a very fine, very detailed shape. Okay. Any idea how to do it from coarse to fine fabrication?
You start in the beginning, then use the simply shape. For example, like a cube or a circle.
Good.
Gradually to optimize this shape to the more complex shape.
Very good.
That is that approach to the original object. Yeah.
Okay. So, did you hear any constraint or conditions how to make the shape from coarse to fine? You need to consider what conditions. Do you remember?
No, I won't.
Okay. So, any other students remember when we apply coarse to fine approaches to reshape the model, what conditions we need to apply? For example, we need to consider the symmetry of the objects. Oh, okay. So when we make the shape from a cubic to a very fine structure. Any other conditions you heard? All right. Today, I would like to introduce very useful AI tools that can help you understand the talk, the course, or the meeting. Okay, so it's called Notebook LM. If you search the keywords by Google, then you can go to the front page of this. Okay, so here we can press to build a new notebook. Okay, and then we can choose the video. For example, our video is course, to find fabrication with video. Okay, and then it will process this video and produce a lot of useful information to help you understand the content. So maybe let me go to this one. I already created during the afternoon. Okay, so here we have some summaries here. What is this video clip talk about? What is the process, of course, to find 3D object fabrication? Okay, so you can see this is the source video. Okay, so actually it can transform the audio to text entirely. Okay, so you can see the entire text. Okay, and a little bit summary of this video. All right, and then we have other tools to help us understand the content. For example, we have the summary by audio, summary by video. So let's see this is the audio summary.
哎，欢迎收听。哎，你有没有想过，如果我们要3D 列印一个非常非常大的东西，比如说一个真人大小的雕像，或是那种特殊造型的家具，可能会卡在哪里啊？直接印，那时间跟材料费，可能会吓死人吧？
对啊，这就是现在3D 列印技术，要放大尺寸的时候，一定会碰到的一个很现实的物理限制。你想想看嘛，
Okay, so it sounds like a podcast. Two students, for example, male and female, they talk to each other and discuss about the video or the technology of Coffee Fab. Okay, so during the conversation, maybe you can understand this more when you are walking, when you are taking the bus. Just listen to the content, you will understand more. And of course, we may have some report. For example, we can produce a report of the content. What is all the details or the structure of this talk? How these large 3D objects can be created, even by analyze its advantages or disadvantages. All right, so maybe let's see some tests. So I will give away extra points for you if you answer the question correctly. Okay, so here. All right, the first question, according to this method, what is the goal to fabric the large 3D objects into its interior basis and the outer part? Okay, A, to apply more color, B, to enhance the strength of the total structure, C, to reduce the cost and time of the manufacturing, D, to make the final objects waterproof. C, okay. Okay, one extra point, you can go to TA after class. Okay, next one. For this Coffee Fab objects, how to generate this interior basis, which is very rough and they have so many different faces. A, you can use 3D printing to generate a low resolution interior basis. Okay. B, you need to carve this basis from some material. C, you can use like a frames, okay, which is pre-generated frames. Okay. D, You can use some flat material and use laser cut and assemble a low 3D plate. Okay, so how do we produce the interior structure of these objects? A, B, C, D. D. All right. So I don't know if this question too simple or you understand this video very well, but anyway, you can try this by yourself because last week we provide video recording for our course. If you don't understand anything, you can try these AI tools to help you understand our pre-recording course. Good. All right, so maybe let's go to the course last week a little bit to summarize. If you have you studied the course last week, because DCT is, I think it's not most difficult part, but relatively difficult part of our course. Okay, so maybe we can jump to the knowledge graph first. Okay, so let's see. This is the knowledge graph. Okay, so maybe we can go to DCT and expand the tree to see more terms if you can explain these terms by yourself. For example, when we talk about DCT, actually we transform the spatial domain to frequency domain. What does that mean? If we have image 8 by 8, we just talked about the basic unit pixel, right? So the smallest unit of an image is pixel. And we use grayscale 0 to 255 to represent the intensity of this pixel. For example, this number is 10, the next number is 100, the next one is 255. And we can have 64 different pixels and different intensities. So we call this spatial domain. Why we call that spatial? Because it's a matrix, it's a 2D spatial representation. So we call that spatial representation. Okay. Then we transform this spatial domain to frequency domain. Okay, so last week we introduced DCT to transform this spatial representation to frequency representation. So our spatial domain to frequency domain. So anyone can summarize what is frequency domain for us? Because we know spatial domain is a 2D matrix. It represents the distribution of all these pixels on 2D plane. So we call that the spatial domain. But what is frequency domain? Frequency domain. Okay, anyone could use like simple words, 2 or 3 sentences to explain what is frequency domain.
Left top corner is the average brightness.
Mm-hmm.
And你越往右下走的话，它就从低到高频的那个频率的那个模式。
Okay. So we mentioned low frequency from left top corner to high frequency, which is close to right bottom corners. How do you determine which one is low frequency, which one is high frequency? Okay. Yes, that's the definition of frequency, the rate of color change. But he talked about the low frequency is in the left top corner, and when we move to the right bottom corners, we move to high frequency components. Why? Why it has such a distribution? Here is low frequency. Here we have high frequency components. Okay, so if you remember our DCT components, when we apply DCT to A by A components, actually we have 64 different frequency components. For example, this one, you can see there's no change about this component, it's all white. Okay, but when you go from left to right or top to bottom, you can see we have vertical and horizontal changes when we move from left to right and top to bottom. Okay, so in the end, you can see this component, we have a lot of changes along vertical and horizontal directions. So it's just like a chessboard, right? We have black, white, and so on. Okay, so because based on this order of DCT components, we call this low frequency components because the change is very low. But this one, the frequency is very high, like white, changes a lot vertically and horizontally. Okay, so that's the reason left top corner represent low frequency component, and right bottom corners we have a lot of high frequency component here. Okay. So let's go back to this question. When we have such components, so one is frequency representation. How we transform spatial domain to frequency domain? Okay, maybe we can answer the first question. For the original images A by A, actually we have 64 different grayscale values or 64 pixels. So what is the results after DCT when we transform spatial domain to frequency domain? What is the resolution of the DCT data? Originally it's 8 by 8. After DCT, what is the resolution? Still 8 by 8, right? Okay, so originally we have different grayscale, 10, 100, 255. So what are all these values in DCT representation? If we still have the resolution 8 by 8 for frequency domain or frequency representation, what are all these values? 2 extra points. Any guessing? Okay. So what's the value of this? For example, it's 12. I don't know. How do you know the value of DCT representation? By the formula, okay. So maybe we can go to the formula. We have a lot of formula, f of u and f of r. So what value you are talking about? F of u, okay. So that's right. Good. So when we transform 2D images using DCT, actually we are calculating the linear combination coefficients for all these frequency components. For example, in this case, we have 8 different values or 8 different pixels. Okay. Then by 1D DCT, we will use 8 different frequency components for linear combination. So you can consider this one, this one, this one, this one. They are all bases, just like the 2D version. A by A, we have 64 different frequency components. Here, for A pixel data or signal, we only apply A different frequency components. They are represented by different cosine waves. Okay, so once our signal is, the dimension is 8, then the number of frequency component is fixed. It's also 8. So next question is, if we have this 8 cosine wave, what is the linear combination coefficients? For example, you can see we have like black, 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 and white, gray and white, and other pixels. How do we use this 8 frequency components for linear combination? Then we can create exactly the same results for our input signal like this. Okay, maybe we can consider the simplest is, okay, so for example, our 1D signal is white, 255. Okay, they are all white. There is no change, they are all white signals. So what is the results of linear combination? Maybe we apply this basis more than the others. Because for other components, you can see the frequency of the other components increase gradually. Okay, up, down, up, down, up, down, up, down, up, down, and it changes faster than the others. So we have a frequency component no changes, and we have changed very fast components. Okay, so when we apply linear combination to use these A components to reconstruct the original signal, maybe we use the first components more than the others. So we must have a larger coefficients for first components. So maybe this one is 0, 0, 0, 0, 0, 0, 0, 0. Maybe this one is 255, for example. Okay, so in this case, we just transform the original 255 from 8 dimension 1D signals to another 8 values. These 8 values correspond to the coefficients of linear combination using all these components. So first one, maybe we use 255 as its coefficient. Others, we use zeros. Okay, so this is how we transform from spatial domain to frequency domain. Because for this 1D signal, when we use DCT to represent its results, then we use the linear combination coefficients to use this representation instead of spatial domain. So he just talked about we can apply the equations here. Okay, once we can apply this equation, we can transform the input number 0, 0, 0, 153, and so on. We have 8 different 1D signals. Then we can transform by f of u this equation to transform the original 8 values to this one. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, we still have 8 different values, but actually they are the coefficients of linear combination using these DCT components. Okay, so you can see the first one, the coefficient is larger than the others. It's above 300 more. Okay, so that's what we talked about from frequency domain to spatial domain to frequency domain. Later on, like Unit 4 or Unit 5, we will see another domain which is called time domain. Okay, so in the course this semester, you will see how to represent multimedia by spatial domain, frequency domain, and time domain. Okay. All right. So Hope you can check this keyword by yourself. What is DCT and what are the important properties of DCT coefficients? Okay, because you can see the very important properties of DCT coefficients, which is called energy concentration. So we have very special name for these coefficients, DC component or AC components, and then they have a very special properties, energy concentration. You definitely will see these terms in midterm examination. So I hope you can examine the knowledge tree by yourself to see if you understand all these terms. If it is difficult for you to understand the pre-recording course content, it's okay because we have a lot of different tools to help you understand the course content. For example, we have seen.
嗨，欢迎收听。
Okay, this is also a podcast, and then you can see the a report that summarizes these technologies. Okay, so maybe it will be easier to read this Chinese document to help you understand what is DCT. Okay, maybe you can try yourself by starting cards. Okay, so let's see what is starting cards. Okay. It seems like it doesn't work, but I hope you can try this by yourself. Okay, because we will upload the video every week, so if you have something to understand or you need to clarify the concept of the method, you can use these AI tools. Okay, today let's move on to the next topic. Okay, so let's see different color models. Okay, so color is composed of electromagnetic waves. So you can see different waves, blue, green, or red. Actually, we have three different characteristics of colors: the hue, saturation, and luminance. The hue means the essential colors. It's red, green, or what, or blue. Okay, saturation means how thickness of the color, because it could be light red, right? Very close to white, and it can be so red. Okay, so the saturation means the thickness of the color or color purity. The last component is luminance, the lightness of the color. Okay, so let's remember the three characteristics of colors. Next, we will see different color model: RGB color, CMY color, HSV, and 1IQ. Okay, for RGB color model, actually it's an additive color mixing model because we just mix three different components, red, green, and blue, with the amount R, G, and B. Okay, so you can consider we have three components and one portion of this component to mix up together to have the color C. So we can adjust the ratio RGB. Okay, it's the relative amounts of these components. Okay, so if you open Painter by yourself, actually you can adjust the amount of RGB channels to 255 or 0, 0. Okay, so if this is the random amount of these three channels, then you can see the red channel we have the largest amount, 255. For G and P components, the amount is 0 and 0. That means we have no green, no blue colors, only the maximum amount of red. Okay, so in this case, you can see actually the term 1 just related to color B, because this is the brightest colors B. Okay, we have the largest amount of red channel. Okay, so next one, 0, 0, 0, which means we have no color red, no green, and no blue. So if we have 3 zeros for these components, then we have the color black. Okay, so I hope you can adjust this amount of colors by yourself to see how we connect 3, 4, 5, 6 to A, C, D, E, D, F. Okay, anyone help us to connect 3 to 6 to A, C, D, F? One extra point. Okay, so if you're not sure, maybe you can see this figure. Okay, this means when we have RGB channels, once we have equal amount of R and G, actually the color is this. Once we have equal amount of R and B, then we will have color like this. Okay, yellow. Okay, so actually we have special name for these colors, but just for your reference, to have the answer here. For example, F, so you can see F is yellow, right? So if for yellow, that means we have equal amounts of R and G, but no B. Okay. All right, please write down your answer on Blackboard. We can show your answer to all students. You can write, for example, 3 to C, 4 to D. All right, let's check if this answer is correct. 3 to F, 4 to D, 5 to C, and 6 to A. Okay, so if you compare to this figure, actually you can see yellow, we have equal amount of R and G components. For this one, we have equal amount of G and B components. So maybe we can verify this two first. So for yellow is F. Okay, so we have equal amount of R and G. Okay, so which means 3, right? So 3 goes to F. And how about A? A, we have 0 components for R and equal amounts for G and B. So it must be 6, right? So 6 to A, correct? So next we have 4 and 5. Okay, so let's see 4 and 5. If you compare 3 to 5, You can see 3 is F, right? And we keep the red channel with equal amount 285, but we decrease the component of green to half of green channels, 255 to 125. So how this color becomes, okay, if 3 is green, okay, and yes, that's right. So 3 is F, okay, so okay, maybe let's see this. When we have the one which is pure red, 25500, and when we increase the amount of G and B, so what happened when G and B from 00 to 255 and 255? Okay, so this one is pure red, right? But if this value goes larger, both components goes to, for example, 100, 200 to 255, and it becomes white. So actually, if we increase both channel with equal amount from 0 to 255, then the color goes from red to white, right? So that means if the amount of green and blue is 255, that's just half of the way from red to white. Okay, so you can see maybe it's a gradual process, goes from red to white. Red, little red, very few red, and to white. Okay, so maybe we can see maybe number 4 is something between white and red. Okay, so actually D. Okay, because D is also red, but the saturation is not as saturated as B. So this color we can also consider is red. Okay, so number 4 is D. Okay. Okay, if we have number 4, then we have number 5. Okay, so compare number 4 to number 5. If 4 is D, then we just decrease the amount of green channels, blue channels. Okay, so we only have one thing left, which is C. Okay, so I hope you can try this by yourself to open Painters in Windows. So when you adjust the RGB amounts, you can create all different colors. All right, you can go to TA after class to get 1 extra points. Okay, next let's see the RGB cube. We have normalized amounts of RGB model. Because we don't use 255 to 0, actually we can divide all these values by 255 to normalize the RGB values to 0 to 1. Okay, so our origin is 0, 0, 0, which means black. And when we increase the channel of green to 0, 1, 0, that means we have the maximum value of green channels. So this points means green, and we have red and blue. Okay, now we can see the 3 special names, magenta, prime, and yellow. Okay, that's the name for these 3 colors. Okay, so when we have equal amounts of R and G, then actually it's yellow. So the color yellow, okay, in here. So you can see here, for yellow, we have 110. The maximum amount of green and red channels it creates the color yellow. Next, once we have these RGB color models, then we can transform RGB colors to grayscale easily. Okay, because for grayscale, if you remember, originally we used 8-bit to represent the intensity from 0 to 255. But for grayscale images, usually we can still use 3 channels to represent the grayscale images by L, L, L. Okay, so these values are all the same for 3 channels. And we can use this equation, L equals 0.3R plus 0.59G and plus 0.11B to transform the original RGB colors to grayscale images, just like this. Okay, so here we have 3 channels RGB. However, by this equation, we can calculate the R the L intensities. Okay, using this equation. Then we can transform the color images to grayscale images like this. Next, let's see the advantages and disadvantages of RGB color model. So the advantage is the computer monitor can be engineered to display colors by varying the intensity of RGB components. Okay, so when we want to display different colors on our LCD monitors, it's easy to adjust the amount of RGB components. Then we can display such color. Let's see the disadvantages. There exist visible colors that cannot be represented with positive values of each RGB components. Okay, so that means if you remember RGB color model, we have the color C equals the ratio or the amount R times the component R plus the amount G times the component G and the amount B times with the blue components. So we call this a predictive model when we change RGB to 0 to 1. Then we can vary this amount of 3 channels. However, we still have some colors that cannot represent by positive numbers of RGB. For example, we know R is the red is 100. This is red. Alright, but we may have the color which is, for example, minus 0.5, minus 0.1, and 0. It's some visible colors we can see. However, we cannot represent such colors by RGB models. Okay, so for visible colors, RGB model can just cover one part of all visible colors, not all. Okay, so it's disadvantage. So it's necessary we need to saturate something, okay, to minus something. So this brings us to CMY color model. Okay, so let's see CMY color model. Actually, we have subjective color models that minus something. For example, 1 minus R is C, N equals 1 minus G, and 1 Y equals 1 minus B. Okay, so here we use 3 primitives, cyan, magenta, and yellow. So that's the reason when you go to the printing stores and you print the post. Okay, so you can see these 3 colors along the paper on the edge if you watch it closely. Because when we go to the printing stores, we print the post. Usually we use these 3 primitives, cyan, magenta, and yellow. Okay, then what is C and YK models? Okay, so we use the maximum amount of these three primitives and combine to black. Okay, but actually it's just produce dark brown in the middle of these colors. So you can see this part is dark brown, not pure black. Okay, so here we need to include additional component K. Okay, so that makes C minus K, N minus K, and Y minus K to new three primitives, C and Y. Okay, so this is C and Y color model. Next one, let's see HSV color model. Okay, so if you remember RGB color model, we have the origin black, and we have some point, green, red, and blue, and another 3 points, fire, magenta, and yellow. Okay, now I need you to consider this is a cube and put it on the table. Then we use the black points to touch to the surface of the table and make this cube standing. Okay, so I don't know if you can transform this to this one. Because if you put this cube to the surface of the table, then this surface is attached to the table, right? But here, we just use 1 point of black to make this cubic standing on the surface of the table. And then we push all cubic down to the surface of the table. Okay, so originally it's 3D, but when we push all cubic to the surface of the table, then it becomes 2D. It's just a flat region. Okay, so after that you can see color black is in the middle or in the center of this area. And we just push red, green, blue, and yellow, cyan, and magenta to the surface to make it polygon. Okay. Okay, then it gives us the shape like this. Once we push this cubic to the table, okay, this gives us HSV color model. Next, let's see how we use this shape to represent HSV colors. So the first component is hue. That tells us what color it is. Okay, so you can consider maybe you have a point from the center and pointing to different colors. Okay, so the point can rotate to, from the degree 0 to 360. When it goes to 0, then it points to red. Okay, so if it goes to like 45 degree, no, it's 60 degree, then it points to yellow. Okay, once you have a rotating point, pin, then you can referring different colors. We call that hue. Okay, the next one is saturation, a function of color distance from the center axis, range from 0 to 1. Okay, once we have the point to the color red, we can adjust the length of the pin. Okay, so 1 means the saturation is full. Okay, is so red. And then maybe you can adjust this value to 0.5 or 0.1 to make it less red. Okay, that's what we call saturation. Okay, the last one is brightness of the colors. Okay, so originally we were talking about with just a 2D polygon of these 6 colors. However, we can also like draw from the center of black down along Y and Z axis. Okay, so we can make it a 3D model. Okay, So that means, except for colors, we can also assign the brightness of these colors. It also goes from 0 to 1. If it goes to 1, that's for white, 0 for black. Okay, so we call this model HSV because actually we are assigning hue, saturation, and value. That's the first character of H, S, and V. So we call this HSV color model. Sometimes it's also called HSB because B means brightness. Okay. Okay, next one, let's see YIQ color model. It uses a lot for image compression and video compression. So YIQ, actually, let's see the keywords. It captures luminous components and chrominous components. Okay, so we have one luminous component Y, that means the brightness of the color. And we use two color components, chrominous component I and Q, to represent how the saturation of these colors I and Q means the color components. So for this model, we have one component for luminous and two component IQ for chrominous components. So we can use this 3x3 matrix to convert from RGB to IQ. If we have the RGB values, for example, 2500, when we times this 3x3 matrix, then we can transform its value to YIQ. Okay, so the conversion is very easy.
If the matrix is not invertible, then how will I process the matrix?
You mean the 3x3 is not invertible?
Yeah.
Okay. Here we just transform from RGB to YIQ, so we won't use the inverted matrix for this conversion. However, if you want to convert from YIQ to RGB, then you need to times inverted symmetric matrix here. So maybe you can verify yourself. This matrix is invertible. All right. Okay, so next, maybe Unit 3, you will see different color models, for example, YUV or YCDCR. So that's kind of extension of YQ models. Still, we use luminous component Y and chrominous component CE and CR for image compression or video compression. The last one is CIE color model. So maybe we can see this figure first because we are talking about there are some visible colors that cannot be represented by addictive model RGB. Okay, so let's see the range RGB color model can represent. It means the black one. Okay, so here. So we use RGB model to represent colors within this area. Okay. And we also see CA1P models. You can see they have different range of visible colors. But overall, we need CIE color models because CIE color models can cover all visible colors. Okay. Okay, let's see CIE color models. It's a standard color model to represent all visible colors called CIE XYZ. So you may see this name a lot when we use color models. Okay. Here we have x-axis as the wavelength and lambda as the range through colors of visible spectrum, and y-axis is relative amount of RGB light energy. Okay, so you can see actually the wavelengths of RGB is different when we see the spectrum of these wavelengths. All right. So for CIE color model, we have three primitive X, Y, Z. Okay, so we call this primary colors. And the three primary colors X, Y, Z are purely theoretical than physical entities. So actually we can use this transformation to transform RGB to XYZ. It's a linear transform from typical RGB. Of course, you can use the inverted 3x3 matrix to transform from XYZ to RGB. Okay, let's discuss some properties of CIE color model. The CIE XYZ model has three advantages. The first one is it's device independent. No matter you use LCD or other display devices, it won't affect the results of CIE XYZ color model. Okay, and it provides a way to present all visible colors. We just talked about it. And the representation is based upon a spectral photometric measurement of colors, just like how we measure the wavelengths to have three primitives of CIE LED colors. Okay, and one important disadvantage of this model is it's not perceptually uniform. Okay, so what is perceptually uniform? Okay, so maybe this is the CIE color space. Okay, so when we have take red for example. Okay, so maybe it goes less red or white here. Okay, so we already know red is 255.00 in RGB color model. And we also note, for example, 255, and 255 is white in RGB color model. I'm trying to talk about if this color is red and this color is white. And this color is something in between, just like 255, 125. Okay, 255 and 125, 125. Okay, so you can see the first component is the same, and the second and third components just goes from 0 to 255 and change gradually. Okay, so when we talk about perceptually uniform, if the distance of these three colors are the same, okay, so maybe the length of this part and the length of this part is the same, then we call that perceptually uniform. Because this color just half of this one and this one. If the distance is the same, then we call that perceptually uniform color space. So because it's the advantage of CIE XYZ, that means even the color is just half of these two, but the distance is not perceptually uniform. So let me give you a correct distance. Okay, so it may like this. Okay, this is 255, this is 125, and 125. Okay, so this is the color just half of between red and white. So you can see when we go back to our RGB color model, the value just half of red and white. But you can see This this color, the location is here, very close to red. Even though the color perceptually is just half of them, but the distance is not very correlated to the distance or the value of these colors. Okay, so that's what we call it's not a perceptually uniform color space because visually it's just half of them. But when we calculate the distance, this one is very close to red. The distance is not cannot reflect the visually perception of these colors. Okay. Can anyone translate to Chinese for us? Like 3 or 4 sentences? Okay. 对。嗯。嗯。对对对，好好，就这意思哦，好。对，我怕大家听不懂哦，好，没想到大家理解能力都这么好，真是太好了，好。Okay, so due to this disadvantages, so we have other color model, CIE LAB and CIE LUV. Okay, so maybe you can see the detail. Is one of them is subtractive model, and CIE LUV is an addictive model. That we can improve the original drawback of CIE XYZ model. Okay, let's see some examples of different color models. This one is the original color photograph, and will be represented by CILAB. Okay, and we can choose the component intensity here. And then this is the HSV color model. We just observe the shadow V. Okay, because V is the brightness. Okay, so you can see we don't see any color in this image, just the brightness channel of this color model. And HSL and other color model, luminous part Y. Okay, so CILAB, L, and intensity and the value or brightness or lightness. They are all different. They are all brightness components for all these color models. Okay. All right. Any question for this part? If no question, let's take a break for 15 minutes, and then we can go back to see vector graphics.
家暴，对，家暴。换你。你要不要去外面吗？如果有人用 Mac 开过，就会拉屎。就是拉个对，我的音就长这样。学姐也很酷。啊，一直过。这是我们新中的在上面。没有，这是你打的。这是我打的，还是这个？这可能我看起来像是举例分打，因为这边是这里。那应该是下一个。这里地方一打。好，看一下。那我同时间好像有啊，我在上学。哇，你们很快哦。对啊，应该没有卖到。我拿到了，就是不知道还会还有。你要是录。哇，我刚刚是这样子的。这种回忆，就是完全看，我有在看那种叫回忆。真实的不同算法。我们比那个比较。那我就选这个。好的，还没找到。你的这种。哇，然后这是有关的解释。哇，你会用远端的，好棒。我为了生存，还是学习很多奇怪的技能。你用的远端的。我的远端是，我的远端是我回家用那个在我做这些东西的时候才要用。好可以哦。对，那你那个很好，所以然后做多火锅店。对。反正就是学生很快，然后还蛮多。都你不知道，这个东西。但是下次可能话，因为其实应该有一个线下来，但是它有它都先把它收掉，然后让它变成一个可以分享的东西。就伪造数据。对，讲话你要说话。我没想到你在这边有这个自己高三就觉得你我说我做不完就把那个全拿过来。太难了。很危险。不然当名人，不然会被我。这样就这个感觉超麻烦。反正我真的用不出来，我就是想找办法。但是说有时候人平台，就包括我说。你那个完全没有。看这个哪个叫做好。等一下。对啊。唉，我写了4个。 但是说就很怪，就蛮蛮写实的。
什么东西啊？那个社团，我看到上面干嘛？反正就是举最强。
对啊 g r a d y 是找最高，这个是最高的。就是那种比如说走一条路都在看成功几率，然后这个就是看一条路的成功几率最大的，这个就是然后这个就看比较复杂。
说阿姨，
然后这个是主要上，
你
这主要是买一个，就是剩余一块。
好越低啊。那为什么这个是？为什么你们研究都有7？
对啊，
为什么你不是愿意用？
对啊，他就是弄得越大越
到稍微往下，用的越往下。
啊，就是这样。
你用的越多，你就越
你想我怎样？就这样。
这是你的心理层次，好怪。
我不知道啊。想到
这个是
request 越多，所以 request 乘以的越多。
好嘛，
这都是跟好好
你刚刚做 SPF，
嗯，
那你当初最短。
差不多。这两个就很好大家，不然差一点点。然后玩的
要不然全市场就是特殊设计。
这是什么？
你看他 scan 出来进来是这一。
开始什么玩的？你发个顶不出来就开始。70几块就让下手。
对吧？就有点。
哦，我下一次想要就是你知道吗？就是比如说弄的有10个，然后你再做20个弄的时候，就是帮你原本的10个这样子。那你这样这个感觉，那你们应该有办法，就是你们好像也会有听到这种。
用过。我唯一有玩过的10个手机。美国他们都很难接。有好可以用阶级知识。这个不是之前学长的论文吗？不是论文，他们去年的专题讲过，他们用过的方法。
都不是这个学姐的意思，学姐的意思。
我有白针。我不知道他做什么。为什么他都有开什么条件？他是没有开条件。我也做了，我已经做成。那你多难受？哇，麦当劳，叫麦当劳，下雨，他为什么他的桥梁？听起来很新。有啊，我妈要给他买乔迁礼物，要买乔迁礼物给他。没有吧？谁看的？没有吧？不是他跟我说。我们很闲，让我们那个。就我们现在。啊，就是。他是有叫我们，他叫我们，他有，他有叫我们去用的。 应该是我猜是你们他们一年只开50后。对啊，一年只开50后，超累。对啊，他们想去看就是很高的。因为我把他们说的。我们也不用位置了，我觉得可以下班。对啊，就我们你有那个？好像二座还是3座？好像可以做2座。我们是开始。我好像你们。没有，我觉得我蛮庆幸的。他操我逼，他操我逼，我觉得操。对啊。超感。他真的是觉得。我说他超前。
All right. Next, let's see the topic: vector graphics. It's image format suitable for pictures with area of solid and clearly separated colors, cartoon images, logos, and so on. Just like when you open the Word or PowerPoint, you can choose the components, for example, rectangle, and you just press your mouse and drag, then you can assign the size of the rectangle. They are all vector graphics. You don't have to assign the pixels, right? Pixel by pixel assignment. You don't have to do that. You just press and drag, and you can create, for example, circle or triangle. Okay, so that's vector graphics. We call that area of solid and clearly separated colors because usually we can assign the same colors for all regions. Just like you can, for example, use the brush and you choose the color and press here, and it's all pink in this area. Okay, so vector graphics is suitable for solid colors. It's just not like natural images. We have a lot of changes of pixels because for the lighting conditions, maybe some is dark, some is light. But for vector graphics, usually they have solid areas or solid colors. Okay, so maybe we can compare bitmap with vector graphics when it grow and shrink. Okay, you can see the results is bad by pixels because when bitmap is enlarged or shrinkage, then we have a lot of artifacts along the edge of these objects. But vector graphics is okay because you can drag these objects to be large or to be smaller objects, but the content still looks very good. Okay, and the speed faster to create and very hard to edit because you need to have pixel by pixel assignment to change the color of each pixel. Okay, so it's relatively difficult for editing. But for vector graphics, it's slow to create but much faster to edit. Okay, applications, Painter, Photoshop, PowerPoint, or Illustrator. Okay, maybe we can see the examples of this vector graphics and beam map. Okay, so when we grow this image large and shrink it to be smaller size, for vector graphics, you can see the results is very clear. For vector graphics, it creates a lot of visual artifacts here. Okay, now you can see for different applications, you can use either BMap or vector graphics. For natural images, of course, we need to use BMap because it's not solid color, solid region, and we have a lot of changes for each pixels. But for vector graphics, like the stickers of line, usually we can use vector graphics to create such stickers. Okay, the last part is to use procedural modeling to create the images. Okay, so next I would like to introduce an algorithm how we can use curves to create different images. Okay, so the curves is based on this function y equals f of x. Okay, so actually you can assign different kinds of functions. For example, the square roots of r squared minus a squared. So we have learned that before. This is the equation of circle, right? We have the radius r, and we have the center of the circle xy. Okay, so based on this function, we can draw the circle. We call this explicit function because we know y equals something. We also have the implicit form of the function f of xy equals 0. If we move all terms to the left-hand side of the equation, then we can write this one to be f of xy equals 0. Okay, let's see the parametric form of the curves. Actually, we can specify each pixels using the parameter t. Okay, so when t is varying between 0 and 1, actually we can assign all p of t along the curve. Okay, for example, we have a curve like this. Okay, this is the starting point, this is the end point. We can call this p of 0, and this one is p of 1. Actually, in the middle of the curve, which is p of 0.5. So we can vary from 0 to 1 to specify each position along the curve. Okay, so we call this parametric form of the curve function. Then we can define nth degree polynomial function to fit this curve. Because we know polynomial function is very useful. We have learned y equals x squared plus 2x plus 1. Okay, so we know the curve like this. Okay, right? But also we can have a high degree of polynomial function. For example, if we have y equals x cubic plus 2x squared plus x plus 1, or we may have something like this. Okay, so for higher degree polynomial, then we have maybe something like this. Okay, if the degree of the polynomial function is very high, so we call this nth degree of the polynomial function. The leading term is t to the power of n. Then we have next term t to the power of n minus 1. And we have the corresponding coefficients an, n minus 1, n minus 2, and so on. Okay, next, we will use only cubic polynomials, which means the leading term is t to the power of 3. Okay, so we can write the parametric form x of t as ax times t squared, t cubic, plus bx t squared, plus ext plus dx. Okay, so this is a very standard cubic polynomial function. We can also write y of t. So in this case, we still use cubic polynomial functions, but the coefficient is different for y coordinates. In this case, we use a y, dy, cy, dy to indicate another cubic polynomial function. Okay, next, let's see, we need n plus 1 control point for this curve for n degree polynomials. Okay, this means actually we can define the control point to create such curve. For example, if we have a curve like this, okay, so if this is y equals x squared plus 2x plus 1. Okay, so the leading term is 2, right? So we need n plus 1 control point. In this case, we have 3 control points. What is control point? Okay, so the control point looks like this. We may have the control point here, and one control point here, and one control point here. So when we call that a control point, you can imagine when you drag this control point, the curve will change accordingly to this control point. So if I drag this control point to the position here, then maybe this curve looks like this. Okay, because the curve is changed by the position of the control point. You can drag this point to different locations, then the curve will change its shape accordingly. Okay, so next let's see the parametric curves. We have x of t and y of t. Then we can rewrite these two equations by matrix form. Okay, so if we consider x of t and y of t as 1 by 2 matrix, then this 1 by 2 matrix can be written if we separate all this parameter t using one matrix, and then for all coefficients ax, bx, cx, dx, and ay, dy, cy, dy to another matrix of the matrix, then we can see this is 1 by 4, 4 by 2. So after multiplication, it will be 1 by 2 matrix. So we can see the dimension agree when we rewrite this equation by separating different components. Okay. So here we call this matrix t cubic t squared, t and 1 as capital T, and we give the name of all these coefficients, the matrix C, because coefficient, right? C is the coefficient. So the position P actually is equals to matrix T times C. Okay, next I would like to introduce a very famous method, Bezier curve. Okay, Bezier curve is a parametric curve described by polynomials based on any number of control points. Okay, we just mentioned the control point number is the degree of polynomial plus 1. So from our previous discussion, if our polynomial function is cubic, then we need 4 control points, P0, P1, P2, P3. Just like the example here. For this case, it's the polynomial function by x squared. Okay, so if we have the cubic function x cubic plus 3x squared plus 2x plus 10, for example. Then we may have the curve like this. Okay, so this is the first control point. This is the last control point. So we have P0, P1, P2, P3. Okay, so maybe we have control point of P1 here and control point of P2 here. Okay, so this is one example of Brazil curve. When you draw this curve by MATLAB, you can specify the location of the control point, P0, P1, P2, and P3. Once the location of these four control points is fixed, then we have a fixed curve, which is called my Brazil curve. Okay, next, let's see how do we determine the coefficients. Because the coefficients help us to draw this Brazil curve. So once the control point is given, how do we know the curve looks like this? Okay, so you can specify any location of P0, P1, P2, P3. However, once this location is fixed, how do we know which curve it is? So we need to determine the coefficient of this curve. Because the coefficient is determining, which determines the cubic polynomial function. If we know ax, bx, cx, dx, a1, b1 to d1, then we know which cubic function it is. Okay, so next, let's see how we discover those coefficients. Because we have four different parameters, ax, bx, cx, dx. In this case, we need four equations to help us solve these four unknowns. Okay, so let's see the first condition. The first condition tells us P prime of 0 is the rate of change of lines P0 to P1. Okay, so we can calculate the first order derivatives of x of t. So if it is the rate of change of the line P0 to P1, okay, so maybe you may consider this is a tangent line of this curve. So we can calculate the first order derivatives. It's easy, right? 3 to the front, 3ax. And then we just minus the cubic minus 1, so it will be squared. Okay, so here we calculate the first order derivatives of p prime of 0. Okay, so in this case, t we use 0 instead. Okay, so then we have 2 times bx times 0 and cx, and this one will be 0. Okay, so it will be the tangent of p0 to p1. So we can use p1x minus p0x. And then the y coordinates is 1 divided by 3 minus 0. And we can get the first equation. Cx equals 3 times p1x minus p0x. Because we have 0, 0 for this term. In the left-hand side, we only have cx here. And in the right-hand side, we have 3 times these terms. Okay, this is our first condition, then we can get the first equation. Let's see the second condition. P prime 1 is also the rate of change from line P2 to P3. Okay, so this is the tangent line if we connect P2 to P3. It's the tangent line of this curve. Okay, so you can see P of 3, actually T is 1. Because the parameters t starting from 0 and end at 1. Okay, so we can just calculate very similar to equation 1 to calculate the first order derivatives of this equation. 3ax 1 squared plus 2bx times 1 plus cx. Okay, so this one when we calculate first of all the derivatives and it becomes 0. Okay, and then in the right hand side we have p3x minus p2x divided by 1 minus 2 over 3. Then we can get the second equation. Alright, next let's see, we still have two conditions. P0 is the first point and P3 is the last point. Because when you see the example, we have 4 control points. You can see first control point and last control point, they all lie along the curve. But P1, P2 does not. Okay, so we can use this condition. If P0 is on the curve, P3 is also on the curve, then we can put 0 into the equation to get the position P0x. Okay, then we can put the parameter t equals 1. Then P3 is also on the curve. Okay, so ax plus x plus 6 plus bx equals P3. So in this case, finally we have 4 different equations. Equation 4, 3, and equation 2, and equation 1. Okay, so if we put all these 4 equations here, then we can rewrite these equations into a matrix form and discover the solution of these unknown variables. Okay, so let's see how we rewrite this equation into the matrix form. Firstly, we need to separate the unknown variables A, B, C, D into a vector. Okay, so you can see for the first equation, 1b equals p0. Okay, so we can write this 4 by 4 coefficient matrix 0, 0, 0 here. So in this case, we have the first equation 1 times b equals p0. Okay, that's the first equation. And then for the second equation, a plus b plus c plus d equals p3. So the coefficient of a, b, c, d is all 1. Therefore, we have 1 times a plus 1 times b plus 1 times c plus 1 times d equals p3. Similarly, you can write the resting 2 equations by this form. Okay, so actually you can like multiply the right-hand side. You can see actually it's our original 4 equations. Okay, but when we write in matrix form, it helps us to discover the solution in BCD easily. Because we can calculate the inverse of this 4 by 4 matrix to both sides. If we write this 4 by 4 inverse here, okay, so the inverse times itself becomes identity matrix, so it's disappeared. Then in the right hand side we have the inverse matrix here. Okay, therefore ABCD becomes the inverse of this coefficient matrix times the control point matrix P0 to P3. Okay, so then the inverse of this 4 by 4, you can calculate by yourself. Actually, it is this 4 by 4 matrix. Okay, and then it times this control point equations. So maybe we can multiply them together. For example, 2 times P0 minus 2 times P3 plus 3 times P1 minus P0 plus 3 times P3 minus P2. So you can see this is the first entry of the answer. Okay, so if you multiply the row and column by yourself, actually we can get a 4 by 1 matrix here. Okay, Once you accomplish this step, then you will see, actually we have P0, P1, P2, P3 in this matrix. We can separate the coefficient out of this unknown variables, P0, P1, P3, P2. Okay, so once we separate P0 to P3 into another matrix, then we have another 4x4 matrix here. Maybe we can verify by ourselves. -1 times P0. Okay, so -1 times P0 plus 3 times P1 here. -3 times P2 and 1 times P3. Okay, so if you multiply the first row to the column, then you will get the first entry of this 4x1 matrix. Okay, so in the end, we can see we write it in a matrix form, and the solution is very clear because the coefficient we are looking for, ABCD, is just the coefficient matrix times the given control point P0, P1, P2, P3. Okay, so this gives us the equation. How do we discover the curve given those control points P1 to P3 by this equation? All right, so maybe we can go back to our previous equation. We just have the cubic polynomial function ax times t cubic plus bx times t squared plus cxt plus dx. We just separate all these components t and the coefficient abcd to two different matrices. Okay, so we call this t times this coefficient matrix. However, from the previous step, we already know the coefficient matrix ABCD equals this 4x4 matrix times the control point matrix P0 to P3. Okay, so originally we have T times C, right? If you remember, like 5 pages earlier, we call this T times C. However, here we further separate the coefficient matrix C to N and G. If we call this one N and this one G. Okay, so in the end, our original cubic polynomial function can be written to T times N times G. T is the parameter of T, and N is 4x4 coefficient matrix, and G is the given control point location P1 to P3. Okay, next, let's see the Brazil curve. Now we rewrite this equation to T times M times G. Okay, so the M function, we sometimes call it basis matrix, and G is the geometry matrix. Okay, let's verify its dimension if it is clear. Okay, so for T is 1/4, N is 4/4, and G is 4/2. Because we have P0x, P01, P2x, and P3x. And we also have P0y, P1y, P2y, and P3y. So G is 4/2. Okay, the first column is for x, the second column is for y coordinates. So in the end, we will have T times N times G, the dimension will be 1/2. That's exactly the location of x of T and y of T. Okay, after the derivation, let's see this example, how we use the equations we derive to calculate the curve. Okay, So here, let's see, in this example, we have 4 given control points. P0 equals 2, 7, P1, 3, 8, P2, 3, 5, and P3, 3, 6. Okay, so you can see these 4 control points is given. Then for the zero curve, we need to solve the cubic polynomial equations. Okay, so let's see. One is the parametric equation x t and y of t that use these 4 control points to describe this Brazil curve. Okay, so maybe we can go back to the original cubic equations. Okay, and x of t and y of t are described by different cubic polynomial equations. Okay, and these equations can be written to t times g, t times n times g. Okay, so in this case, we can put our unknown into this equation. Okay, so t is the same, n remains this 4 by 4, but g, we can use this instead. Okay. Okay, just like this. This is the N matrix. This is the G matrix. G is 2, 7, and 3, 8, 3, 5, and 3, 6. You can see the first column is the coordinates of y of these 4 control points. The second column is the y coordinates of these 4 control points. Okay, so t times n times g. Okay, so in this case, we have the coefficient. When we multiply this 4 by 4 by 4 by 1, we have 4 by 1 of 4 by 2 matrix. So this is the coefficient of x of t and y of t. Okay, so once we have the coefficient, then x of t will be t cubic times 1 plus minus 3 times t squared plus 3t plus constant 2. Okay, this is for x of t. And for y of t, we have the coefficient 8 minus 12, 3, and 7. So they are the coefficient for t cubic, t squared, t, and the constant. So in this case, we have solved these 2 parametric equations of the zero curve. Once we have the given control point P0 to P3, then we can use the previous equation to help us discover what is the zero curve of this parametric form. So far, so good. Any question? Do you have any question? All right, maybe someone can summarize this part for us in Chinese. We can quickly grasp the concept of a zero curve function. All right.
就是它，我们是原本是它的那个方程是用 x 跟 y 表示，那我们可以用，就是我们可以把它简单一点用的，就是单纯一个变数题来表示它，然后它把 x 就是把 x 跟 y 转换成用 t 表示的方法，就是它可以写成 t 等于 t 乘以那个4，然后后面就是我们要找到那个 c 它是什么东西。
我们要解的就是这两个方程式的 coefficient， 就是我们讲的 C matrix。ax by ax bx cx dx 还有 ay by cy dy， 好，这是这个 coefficient 的矩阵嘛？嗯。
然后我们有用到4个算是
Okay, could you summarize these 4 principles for us?
第一个是 P 的P 的一次微分然后代变，然后就是P0到 P1，就是 P0到 P1的界，然后第二个是那个一次微分带1的时候，它的协定是 P2到 P3线。然后第三个跟第四个是合在一起，它是说P0是第一个点，因为第一个 control point， 然后 P3是最后一个 control point， 然后用这4个的话，就可以用矩阵把它举出来，然后就会变成剩下面这个。
好，那我再讲一次这4个条件啊。这4个条件的前2个呢，就是说，我们如果把 P0 跟 P1 这一条线连起来的话，这条线呢就会是 P0 这个点的一条切线。这个线是一个弯弯曲曲的 curve 嘛。但假设你把 P0 跟 P1 连起来这条直线，这条直线就会是这个 curve 的切线。所以我们可以用 P0 跟 P1 是它的切线，然后 P2、P3 也是它的切线，来计算它的一次微分的结果，得到2个公式。好，那接下来的2个公式呢，就是 P0 跟 P3 会落在这一条线上。所以我们刚刚的这个公式都是用 t 这个参数来表示的。那第一个点的 t 就是0嘛，最后一个点的 t 就是1。所以如果这2个点有落在这一条线上，我们就可以把 t 等于0跟 t 等于1直接代入这个公式里面。那我们就可以得到2条公式。那我们这样总共就会有4条公式。好 ，Alright, next.
对，然后我们用这4条公式可以把它变成2个矩阵这样子，然后最后就会分解成2个部分。然后原本的 P 是 T 乘以 C， 然后我们把那个 C 分成 M 跟 G， 然后那个 M 跟 G 就是我们刚刚的那4条式子，把它变成2个矩阵相似。然后那个 M 就是前面的第一个
4乘4的系数矩阵。
然后那个 G 就是我们那个 point 它的坐标位置。
对，
然后最后结论就是可以把它变成 P 等于 T 乘 M 乘 G， 然后那些东西我们都有把它都是我们可以找到的。所以我们就会很容易的把它写成，就会把这个函式写成用 T 代表的式。
好，就是这样哦。好，所以实际上我们要找的这2条方程式呢 ，xt 跟 yt， 它已经可以写成这3个乘在一起了。那这3个乘在一起的 t 的矩阵已经有了 ，m 矩阵也有了，就是这个。那我们只差这个 g 的矩阵了。g 的矩阵就是看，实际上你给什么样的 control point， 就把 control point 的 x y 坐标带到这个 g 的矩阵。所以只要有 control point G 的矩阵也有了，就可以把这3个东西乘在一起。乘在一起之后，我们就可以得到我们这个 x of t 跟 y of t 的这2条这个3次的多项式了。好啊，所以在这个范例里面，我们真的也就是这样做啊，把刚刚的 P0 到 P3的坐标点带到我们刚刚的公式里面，来把 P 乘 M 乘 G 真的把它乘出来看看，乘出来之后，你就得到 x of t 跟 y of t 2条方程式了。好 ，OK, so anyone tell me once we have this parametric equation x of t and y of t, how to draw this curve by this equation? If we know x of t equals this equation, y of t equals this equation, how do we draw this curve by this equation? one extra point. Mm. That's right. That's the answer. Because we know the curve is represented by the parameter t. The starting point t equals 0. The end point t equals 1. Okay, once we have these two equations, you can have a lot of points along between t equals 0 and 1. For example, you can have 0.1, 0.2, 0.3 to 1.0. Okay, then you will have like 10 points along this curve. Okay, so when you draw this point along the curve, maybe you can give finer points. For example, 0.01, 0.02. In this case, you will have 100 points along this curve. And in the end, when you draw a map, it will connect all points for you to form a very smooth curve. Okay, so that's the example of Brazil curve. Next, let's see, we have the equation T times G, M times G. Okay, and then we can rewrite this equation a little bit by T times M first, and then times G. Okay, so we know T is this, M is this 4x4 coefficient matrix. So if we times P times M first, then G, we use P0, P1, P2, P3 instead. Then we may have the equation like this. 1 minus T cubic times P0 plus 3T times 1 minus T squared, P1. Okay, so maybe you can discover the regulations of these terms. Because we have two different terms, T and 1 minus T. And you can see its power from 3 to 2, 1, and 1, 2, and 0, 3 for this 4 control point P0, P1, P2, P3. Okay, so this gives us the concept of blending function. Because what we have done from the beginning to the last equation, so we need to discover 4 conditions and 4 equations to solve 4 unknown variables. In the end, we can have the coefficient matrix and we have the final equations. However, what happens if we have different degree of polynomial function? Previously, we used cubic polynomial function, but what happens if the polynomial leading term is 4, 5, or 10? Okay, so in that case, should we repeat the process again, just like what we did to infer the final equation by different terms of polynomial function? So that will be too complicated. So in this case, let me introduce the blending function. We can use arbitrary degree of n polynomials to draw the Brazil curve. Okay, so let's see this blending function. Maybe we have the cubic function above, or we can compare what happens when we apply the blending function. Okay, so let's see, P of t is our parametric function, just like what we did before. Okay, so actually we calculate the summation over k equals 0 to n. N is the degree of polynomial function. If our previous function is cubic function, then n is 3. Okay, so pk times blending kn of t. Okay, so let's see what are these terms. So pk is easy. right? Because in our previous equation, we have P0, P1, P2, P3. So once K equals 0 to n, then we have P0 times blending 0, 3, and P1 times something, P2 times something. Okay, and blending Kn, okay, so we have two index K and N. It's C A K times T to the power of K times 1 minus T, N minus K. And C of Nk equals factorial N divided by factorial K and the factorial of N minus K. Okay, I believe you have learned this equation before, right? For like permutation, right? And combination, we have to learn this before. Okay, so maybe we can expand this function by ourselves to see what are this. Okay, so P of T equals the summation for the index K equals 0 to n. So the first term is P0 times a blending function Kn. Okay, so K is 0, n is 3. So this is the first term of P. Okay, and then plus when K equals 1, P1 times blending 1, 3 of P plus P2 times a blending 2, 3 of T plus P3 times blending 3, 3 of T. Okay, so we have 4 terms. Okay, and then let's see what is blending 0, 3 of T. Okay, if we use the equation here, then blending 0, 3 equals C 3, 0 times T to the power of K. K is 0, and 1 divided by 1 minus T, N minus K. N is 3, K is 0, so we have the power of 3. Okay, so C of 3, 0, okay, is factorial 3 and factorial 0 and factorial 3. Actually, this is 1, okay, so we don't have to run this term. Okay, and then T to the power of 0 is 0. Then we have only 1 minus T to the power of 3. All right. So you can see, actually this is a blending 0, 3 of T. In the end, it will be 1 minus T to the power of 3. So do you find out something? If we have P0 times 1 minus T to the power of 3, actually it's the first term of our derived equation. P0 times 1 minus T to the power of 3. Okay, so if you finish this blending function by yourself, actually you derive this term, this term, this term, and this terms. Okay. So when n is set to 3, actually this blending function helps us to discover what is the final equation when we need to draw the zero function. But blending function is more general because you can set n to other numbers, right? So in this case, you don't have to derive the final equation by yourself. You only need to set n equals, for example, 4. Okay, so it's 4th degree of polynomial function. Then use the blending function, you can get P of T by yourself. Okay, so I'm going to tell you a trick about this blending function using Pascal triangle Okay, because if you observe this Pascal triangle, you can get a coefficient of each terms. Okay, so here we have 1, 1, 1, and 1, 2, 1. If you add this number 1 plus 1, you will get 2. And 1 plus 2 is 3. Okay, 1 plus 2 plus 1 is 3, and 3. And then when n goes to 4, so we can extend 1331 to 14641 by adding 1, 3 to 4. 3 plus 3 is 6. 3 plus 1 is 4. And the last one is 1. Okay, so once you have the cubic, you can extend the coefficient by Pascal triangle quickly. Okay, so in this case, you can see our cubic function, actually its coefficient is 1, 3, 3, 1, right? So maybe you can guess when n goes to 4, what happens? The equation is just 1, 4, 6, 4, 1, right? So you just need to create the other terms, 1 minus p to the power of 4 times p0, and then adjust the power 3 of 4 to 3, 1, 2, 2, 1, 3, and 4 for other terms. Okay, then you can get this the zero curve function quickly without using this splitting function, if you are familiar with this concept. All right, is this okay? All right, next I would like to introduce an algorithm how we draw the Brazil curve. Okay, so because we just talked about once you have the parametric form of this equation, you can change the parameter p from 0 to 1 by different unit. You can choose 10 points between, or you can choose 100 points in between to separate the range 0 to 1 to another t. Then we can get the xy coordinates between the first point and the last point. Okay, this is one way you can draw the zero curve. However, we also have an algorithm for you. You can draw the Brazil curve. Okay, we call this algorithm the Cass-Georgia algorithm. All right, let's see how do we apply this algorithm to draw the Brazil curve. Once this 4 control point is given, so originally we have P0, P1, P2, P3 as our control point. Once this location of this 4 control point is given, then we can draw the Brazil curve like this. Firstly, we can use P0 and P1 to draw a straight line connecting P0 and P1. All right, and then we find the middle point of this line segment. We call that P01. All right, and then we apply the same process to the segment P1, P2, and P2 and P3. You can always discover the middle point of the straight line, P0, P1. The middle point, we call that P12. And the middle point of the third straight line, we have P23. So originally, we have 4 control points. Once we can discover the middle point of the straight line, we can discover 3 group points. All right? After we have these 3 group points, we can connect P01, P12 to form a straight line and find the middle point, P012, as the green point. Okay, similarly, we can connect P12 to P23 as a straight line and discover its middle point, P123, as another green point. Now we just reduce 3 blue points to two green points here. The last step is to find the straight line connecting these two green points and find the middle of this straight line. We call that P0123, which is a red point. Okay, so this red point actually is the middle points along the Bézier curve. Okay, and then we can partition this curve to left part and right part. So now we have 4 points, P0, P01, P012, and P0123. Okay, you can consider this is another 4 control point, so that you can discover 3 blue points, 2 green points, and 1 red point. So this red point, just the middle points of the left part of the curve. Okay, so you can apply this algorithm again to the right-hand side. Okay, so you have 4 control points here. You can find the middle points of this curve as the red part. Okay, so if we apply this algorithm again and again, because once you have this middle part, you can separate to left side and right side again. For right side and left side, you can find the middle of the points again. So we can draw more and more red points. So in the end, if we have enough or so many red points, we can connect all of these red points together. That will be our final Bézier curve. All right? Could you summarize this algorithm for me in Chinese? Okay, most of you are very quiet, right? Do you want to practice how to describe this algorithm in Chinese? All right, please. Yeah. 对。
一直往下做，会有很多分子就会递进成为
对，所以我们取终点之后就会有蓝色的终点、绿色的终点、红色的终点。And then what happens when we have the final points, this red points?
会在P0和P01之间再取一个紫色。
Alright, let's identify what is the role of this red points P0123. Okay, if we have control point P0 and P3, and we have another two control points P1 and P2. So this is 4 control points. This is our final curve. So what is P0123? Yes, that's right. So it's just the middle point of this curve, P0123. Okay. So once you can discover the middle point of this curve, what is the next step? So you can partition the curve to the left part and right part. For the left part, we still have 4 control points. So you can repeat this algorithm again to find the middle point of the left part of the curve. And similarly, you can apply this algorithm again by another 4 control point of the right part to find the middle point of the right part. In this case, you will have the middle point of the right part and middle point of the left part. Okay, and then you can partition the left part to left and left right, right? And you can apply this algorithm again to find the middle point of left and middle point of left and right. a middle point of right left and middle point of right right. And then you can still find the middle points of this part and this part. So you can have more and more middle points along this Bezier curve. So how this algorithm terminates? Can we do the partition as in infinity step? When this algorithm will terminate? That's right. So if you find the middle points, so this middle point is the neighboring points, then we cannot partition more. Okay, so then we terminate this part. Okay, we can partition until we cannot partition anymore. All right, next, let's see. Once we have different control point, then we may have Bezier curve like this. If we have P0, P1, P2, P3, the Bezier curve like this. But if we switch the order, like P0, P1, P2, and P3, even their location is the same, but we will have different shape of Bezier curve like this. Okay, so I would like you to draw the Bezier curve by the given control point using the Castro-Gel algorithm. Okay. And remember, we have 4 conditions, right? So you can combine these 4 conditions with the Castro-Gel algorithm to discover the middle point. So maybe we can sketch what is the Bezier curve given these 4 control points. Okay, 2 extra points. Anyone want to draw the Bezier curve like the given control point was? All right, maybe we have the answer in the last slide. So let me give you a new control point. Okay, how about this one? So you can draw the Bezier curve by the given control point P0 to P3. All right? Anyone want to try this exercise? If your result is correct, I will give you 2 extra points. So could you remind the other students what are these 4 conditions in Chinese? Because we need to use these 4 conditions with the help of the Castro-Gel algorithm to discover the middle points of the curve. And then we can maybe sketch approximately curve given these 4 control points.
P0到 P1，它是那个 curve 的斜线，
对，
然后 P2到 P3
好 ，P0 到 P1 还有 P2 到 P3 都是这个 curve 的切线，它是切在 P0 这个点跟 P1 这个点的切线这样。好，然后呢，这是2个条件嘛？还有没有？好 ，P0 跟 P3 这2个点会落在这条线上哦。好，它是这个 curve 的起点跟终点。好，这个是我们另外2个条件，所以记得只有 P0 跟 P3，P1、P2 是不会落在 Brazil curve 上面的。好，那这是4个条件嘛？那如果再把 Decatur 的 algorithm 帮我们画出这个 curve 的终点在哪里？好，那也许大家可以把这个 Brazil curve 画出来了。好，有没有同学上来画画看？错了不扣分啊，随便画嘛，也没差啊。好，好来来，那我帮你把那个红笔画出来，好，好，那你直接在上面画画看，好。用滑鼠，对。
这样吗？有点丑。
好，那你能不能好？你画的形状大概是这样嘛？哈，那你可不可以先帮我们用 Decatur 加 algorithm 把它的终点先画出来？我们先确定一下终点在哪里。
这个吗？
好，谢谢，过去了哈。有同学可以跑一下 Decatur algorithm 帮我们找一下 Brazil curve 的终点在哪里吗？好，来。好，首先呢，先找，
这应该是一个点。
他先找了 P2 到 P3 的终点，然后 P2 到 P1 的终点，然后 P1 到 P0 的终点，就会画出3个红色的点了。好，接下来呢，这3个红色点两的连线又可以得到另外2个终点。好，那这2个终点的连线的终点，好，那个终点呢就是 Brazil curve 的终点了。好，那所以刚这个同学啊，你刚刚画的那个圆圆的地方好像画成一个形状，但实际上这一个curve必须要通过这一个点才行，这样。好，那这样好，谢谢。好，那你再来帮我画一下。对，假设它的终点要通过这个点的话，那你刚刚的那个 curve 会长什么样子？好，谢谢。好，那我们来看一下，他画的这个线呢有没有符合我们刚讲的条件？好，我们刚讲的第一个条件呢是 P0 到 P1 的这条直线会是这一条 curve 在 P0 这个点的切线，有没有成立？有嘛？好，这条 curve 在这吗？弯弯的在这，那这一条线呢在 P0 这个点刚好是这个 curve 的切线。好，那这是第一个条件。那第二个条件呢 ？P2 到 P3 的这条直线是这个 curve P3 这个点的切线。这条 curve 弯弯的在这边吗？这条线是不是它在 P3 这个点的切线？也是吗？好，所以至少这2个没问题了。好，那接下来呢，我们第3个条件是 P0 会通过这条 curve， 有吗？好。P0 就是这个 curve 的起点，第4个条件 P3 是这个 curve 的终点，也对了嘛？好，那同时呢，这个 curve 还通过了我们利用 Decatur algorithm 找到的终点，好，所以它的形状就是会长这个样子。好，那这就是一个正确答案了。 谢谢。好，也谢谢你帮我们找终点。好，所以呢，同学们，你们可以自己去试试看啊。好，我们期中考的时候就是会这样考哦。好，I will give you a random 4 control point, just like this or this. Okay. So could you draw the Brazil curve by the given control point using 4 conditions plus the middle points provided by the Castro algorithm? Then you can draw the Brazil curve by yourself. All right. So you can see sometimes this curve is very difficult. Okay, it just goes like this. Okay, so I believe these 4 conditions and the middle of the curve will help you discover what is this Brazil curve looks like. All right, let's see any question for the course today. We can repeat by Chinese, it's okay. 大家会觉得太困难吗？今天的课程？好，这个一片槁木死灰，呆若木鸡啊。好，那如果大家觉得有问题的话呢，就是可以用我们刚刚提供给大家的 AI 工具 Notebook LM， 好，回去把我们今天although we provide the English videos, however the tool Notebook LM will translate all this content in Chinese for you and create the summary, create the test, and starting cards for you. I hope this will help you in your studying.
所以期中考试要带尺的吗？
带尺？
对，尺。
为什么需要尺？
不然我们怎么量终点？它看起来是量终点量歪一些就会图形就会差很多了。
我们没有那么精准啦，我只要看到你有把那个终点画出来，所以我经过那个终点就行了。
我在第75页。
好。
这页你在讲。
好。是啊，我们刚刚前面是不是要经过3次多项式的所有的推导过程？先利用这个4条条件找出来4条公式，把这个公式重新改写完之后，能够找到这个 coefficient 矩阵 C。好，那我们最终才能够推导出来3次多项式的公式解到底长什么样子。好，就是这边的主要的就是这边这个 M 矩阵。我们终于找到原来 M 矩阵要长这个样子，带这个公式回去才能够帮我们解出3次多项式的这个贝兹曲线长什么样子。好，那我们的问题就是，如果我们今天的 Brazil curve 是4次多项式、5次多项式或6次多项式，那我就不知道这个 coefficient 矩阵会变成什么样子了。那我变成是要重新跑这个推导的过程。重新去推4次、5次、6次的公式长什么样子，这样会非常麻烦。好，所以我们这边就直接告诉大家一个最通用的方法，好，就是这个 blending function。这个 blending function 呢，只要你把多项式的 leading term 的这个 n 直接带进去，好，假设是3次多项式，那 n 就是3，那4次多项式就是4，10多项式就是10，那我们就可以直接利用这个公式把10次多项式直接用这个公式展开来，我们就会有最后的公式解了。好，那所以我们刚刚讲说，你要展开来这个公式好像有点麻烦，所以你还可以利用这个巴斯卡三角形来帮我们快速得到所有项式的coefficient应该是多少。好，那这样就会变得非常快了。好，就这样。那所以同学们其实回去试试看，假设我们期中考题就是这么简单哦。I will give you n equals, for example, 6. Could you give me the Brazil curve in parametric form, x of t and y of t? What are these 2 equations given n equals 6? Okay, if you know how to explore blending function, you can get the Brazil curve in 6 degree quickly. All right. Any other questions? Okay, if no questions, see you next week.
那刚刚有加分的歌第2名。要保存吗？那个